geometric.
Oh, yeah, sorry. Sorry to interrupt. I was just going to say that the recording is not on, and strangely, I mean the chat. I mean you can't. I mean I wanted to send a message to Alp, and I could not. So yeah. So I mean, sorry to interrupt. I mean there was just a problem with the recording. Thanks.
Okay, no worries. All right. So in the large Q sense, ordinary abelian varieties are the most common, right? Well, what does most common mean? Well, geometrically, if you think of the space of principally polarized abelian varieties, if you think of AG, the space of ordinary abelian varieties is known to be open dense. And a similar thing is known to be true for curves. Right, like so the ordinary locus is open dense, and you know more about like the dimension of, or the dimension of the p rank less than or equal to some number locus, in particular due to work of Faber and van der Heer. I'm sorry if I mispronounced the name. I'm really sorry. Which again, this result has been mentioned earlier during the conference, where you talk about the codimension of the p rank less than or equal to S locus. So for hyperelliptic curves, the same is true. Like the ordinary locus is open dense, and you know more about the p rank stratification due to Glass and Priest in 2005, and so there are also other kinds of curves, right? So there's like Arden-Troyer curves, for which, well, the moduli space is reducible for large enough G. So this, so it doesn't really, so the ordinary locus is not like dense, but it's open dense in one of the components. So those are some sort of like geometric results which seem to say, well, at least the first three seem to indicate that ordinary abelian varieties are the most common in the large Q sense. And there are also some other types of Cohen-Lanster type of results about the distribution of the p to the n torsion group scheme of an abelian variety due to Actor from 2016. So here, essentially, so okay, so maybe I won't say too much about this, but the idea here is that if you fix a geometric isomorphism class for like the symmetric BTN group scheme of that, so for a candidate for a p to the n, then inside that geometric isomorphism class, somehow like the probability that something occurs is like 1 over the size of the automorphism group. So that's what I mean by Cohen-Lanster type. So there's a bunch of like large Q limit results. And so this is like, I'm going to do a hard U-turn over here and say, okay, now let's think about the large G limit results. And so maybe if you look at the first three, you're thinking, oh, ordinary abelian varieties are the most common thing here. And so let's try to formalize the question for large G limits. So the large G limit question is what is the probability that an abelian variety is ordinary in the large G limit? So to write that down more precisely, let's say we fix a finite field once and for all. We consider a set of abelian varieties over K. So I will often call this a family, but it's more, it's not a family in the geometric sense, because you're fixing a finite field, and then so typically we want the set to be infinite. So in particular, the dimension of the abelian varieties, they're going to be arbitrarily large. So it's not a family in the geometric sense, but perhaps more so in the sense of the talk from earlier today, just the previous talk, right? So it's more of a family in that sense. Okay, and so F ord is going to be the subset of these which are ordinary, and we're going to define this, well, this ratio of abelian varieties in this set of ordinary abelian varieties over the set of bounded genus over the total number of abelian varieties of bounded genus, right? So this is like up to genus log x, how many, what proportion of abelian varieties are ordinary. That's what this is measuring. And so what we want to do now is take the limit as x goes to infinity and say, does this quantity exist? And if so, can we calculate it? So that's the question that we're going to ask. And note, of course, that this depends significantly on f, right? So like it depends on what kind of family you pick. We can construct families that are like all ordinary, and so maybe you get probability of 1, or you could pick some that are just not ordinary at all, or never ordinary, and then you can get 0. And so ideally, you want to consider interesting families, right? So the word interesting here is kind of vague, but the kind of things that I'm interested in are like, well, all principally polarized abelian varieties, maybe, but that's like very ambitious. So maybe like all curves or hyperelliptic curves are like a subset of some curves for which this quantity is nice. So to put this in the context of like the last talk, essentially I'm looking for like a family that is asymptotically good. Well, and for me, good means between 0 and 1, maybe slightly more interesting. Actually, even 1 is interesting. But so where the measure of goodness is somehow this sort of a particular P rank, which is in this case ordinary. So the P rank is equal to G. Okay. So you could also ask variations of this question, of course. And so, for example, you could say that instead of doing a usual count, right? So the way I defined this ratio, it was just like the number of abelian varieties inside your ordinary space with bounded genus over like the total ones. And so you could say, okay, instead of doing this, maybe you want to weight all of these by 1 over the size of the automorphism group, which is something that has already come up earlier in terms of doing a stacky count versus a usual count, right? And when you pick your F, you can also pick your notion of isomorphism. You're thinking, okay, am I counting curves up to isomorphism as curves? Am I counting them as up to isomorphism of covers, of maybe a certain gonality, and so on and so forth, right? And so in this talk, I'm going to talk about curves of a certain kind, and I'm going to do like a okay, so when I talk about the curves, I'll say what kind of notion of isomorphism I'm using, but it's not going to be a stacky count. It's going to be what I call a usual count. Okay, and of course, when you do a stacky count, you can choose to weight by the automorphism of the curve or the Jacobian, etc. Okay, so I'll leave it at that. And then, of course, you can ask about different invariants. You can ask about how Newton polygons behave, or some other kinds of like Eckert-Lord strata, or and so on and so forth. You can also ask about the distributions of P ranks, right? So, like instead of just doing ordinary, you can ask about what about some other P rank? Okay, and so there's a lot of variations, but for today, we'll just stick to this. Okay. I should say that if you have any questions, feel free to jump in at any point. I will monitor the chat as well. Okay, so where did this come from, right? So like, what was this work motivated by? So this has to do with equidistribution of Frobenius, which is also something that Alina mentioned in her talk, which is that, so there are these heuristics due to K-Stellenberg and Zurich-Brown that predict the probability that an ordinary abelian variety, that an abelian variety is ordinary. So what they do is they basically say that, okay, what is a random abelian variety? Okay, so maybe you can somehow model the p-divisible group of an abelian variety using the Dieudonné module. And if you say that the Dieudonné module is random in some sense, then what should you expect from an abelian variety? And so what they predict is that the Peter origin of abelian varieties, if it's random in some sense, which I'll say in a bit, then the probability is given by this nice product. And for people who work on arithmetic statistics, this sort of looks like you might recognize this as being very similar to the quantity that comes up in like Cohen-Landstrover function fields. Yeah, except for in that case, you have the L, this is L and not Q. Okay, so what is their underlying assumption? Well, the underlying assumption is that Frobenius behaves like a random matrix. So if you think about the monotomic group of the space of abelian varieties, then you somehow expect that Frobenius behaves like a random matrix that's chosen somehow uniformly from this particular coset of sp2g. Right. So somehow the behavior of Frobenius is governed by the behavior of this group sp2g as g goes to infinity, and then they predict that as g goes to infinity, maybe this is what is supposed to happen, that an abelian variety is ordinary with this probability. Okay, are there any questions so far? Okay, and so you might ask, okay, what is known about like the general picture? And somehow surprisingly little is known, or maybe not surprisingly. Large G limits are hard in general, I guess. And so not much is known. And so in this talk, I'm going to talk about two specific families of curves where you can actually say something about this. And I will also say about why those families of curves behave differently from what Case Hallenberg and Zurich Brown call a random abelian variety. So the two families that I'm going to talk about are Artin-Schreier curves and superelliptic curves. So what is an Artin-Schreier curve? Well, an Artin-Schreier curve is it's a curve with a degree p mapped to p1 in characteristic p. So in particular, you can think of this as having this kind of a model where fx is a rational function over the base field. And so the theorem says that if you take this family of Artin-Schreier curves, then the probability is 0 if p is not equal to 2, and it's some non-zero constant if p is equal to 2. And so this is quite different from the large Q-limit case where ordinary seems to be like the most common case. But okay, yeah. And so, well, at least for p bigger than or equal to 3. On the other hand, for p equal to 2, notice that you get something non-zero. What happens in the p equal to 2 case is that Artin-Schreier curves are also hyperelliptic curves, that the hyperelliptic locus is, well, it's very nice. And so this is, right, so this is what you get. And I should also say that this is not equal to the ESZB prediction, the CZB prediction. And because their constant is like 1 minus q to the negative 1 plus something, and it doesn't agree for several. If you try to approximate both of these with the computer, you don't get the same thing. Okay. So the other thing I want to say over here is that somehow this count is not the way it's proved. It's not a count up to isomorphism of curves. It's more up to an isomorphism of covers of P1, which means in particular I'm counting curves with a map to P1. However, if you try to count up to isomorphism of curves, then the same is true at least for p bigger than or equal to. So So for isomorphism of curves, count. Same is true for p bigger than or equal to 7. So 0% of these curves are ordinary. Okay. And so the next thing is about superelliptic curves. So superelliptic curve is something that looks like y to the n equals fx, where n is co-prime to the characteristic of the field, and now f is a legitimate polynomial, not a rational function. And we let S and G denote the moduli space of superelliptic curves of degree n and genus G. And so now let n be some odd prime and q a sufficiently large power of 2. Then Fn, so if you let Fn be like the set of all superelliptic curves, then the probability that something in this family is ordinary is 0. And so note here that for superelliptic curves, there are two ways to increase the genus. You can like increase n and get like a tower of curves, or you could, or you can increase the degree of f in y to the n equals f. And so here we increase the degree of f. Okay. And so some quick observations. So Artin-Schreier and superelliptic loci, these are thin subsets of the modular space of curves, right? So for example, Moget showed that the Artin-Schreier locus is dimension 2g over p minus 1 minus 1. So this is like much smaller than the modular space of curves, which is 3g minus 3. So it's not like the generic case anyway. There are also curves with large automorphism groups. So in particular, you shouldn't expect that statistics to be governed by SP2G, right? So you shouldn't expect that calculating a heuristic for SP2G should give you something that says that predicts the number of the proportion of ordinarity for Artin-Schreier or superelliptic curves. So far we haven't violated the CEZB heuristics. But sadly, what it turns out is that if you sort of, maybe for Artin-Schreier curves, it's a little trickier, but at least for superelliptic curves, maybe you want to say that unitary groups govern the statistics of this kind of thing, right? In the superelliptic case, and it turns out that that doesn't work either. But that could be a low characteristic issue. I'm not sure, mostly because nothing has been proved for higher characteristics, right? So characteristic 2 is like the only where we can actually prove something and verify that something is true or not true. But right, so that's one issue. Okay, so right, so now I'm going to go on to the proof of these results. And in particular, maybe you're asking yourself, why these families? Like, why Artin-Schreier or superelliptic curves? Why are we measuring, like, why are we trying to figure out whether these, or what lets us figure out whether these are ordinary asymptotically? And the key property that we exploit is that the criterion for ordinarity is determined by local combinatorial data. So what do I mean by that? So the way these proofs progress is, okay, so what are we trying to calculate? We're calculating the limit as x goes to infinity of something that's the numerator over the denominator. Oops. Right? And so we individually calculate the order of growth of the numerator and the denominator, and then divide the two. And okay, so that's basically the way this goes. And so if we want to calculate the numerator of, say, of whatever we're doing, so essentially we're trying to calculate the sum as n goes to x, for n less than x, of an, where an is the number of curves of, let's say, genus n, right? And what we want is, well, okay, the only one of the big ways in which, one of the standard ways in which you calculate something like this is by using a Tauberian theorem on the corresponding Dirichlet series, which you get by doing this, q to the negative ns, right? And so essentially, the way the proof progresses is calculating these Dirichlet series, and proving analytic properties of these things. And it turns out is that for Argent-Schreier curves, this ZS for the numerator and denominator, these have very nice Euler products. Everything sort of behaves very nicely in terms of local factors. For superelliptic curves, this is not quite true, but we can get away with just proving bounds for the numerator and denominator. And so that's essentially what goes into this, the fact that somehow all of this, a lot of like this information is captured just like combinatorially. Okay, so how is this actually captured combinatorially? So let's just see what happens for, let's say, Argent-Schreier curves. So if you write down an Argent-Schreier curve, let's call this CF, where this is y to the p minus y equals f. And so the ramification data controls both the genus and the p rank. And so to write this down more precisely, if you write f in terms of a partial fraction decomposition, you take these, so where this is like f alpha, x alpha, where x alpha is given by this, right? So you decompose it in terms of the partial fraction thing. And without loss of generality, you can take f alpha to be p's power free, right? So this just follows from the fact that your curve looks like y to the p minus y equals fx, and so you can like remove p's powers. And so the Riemann-Hurwitz formula implies that the genus is given by this quantity, where, right, so you have a p minus 1 over 2 times this whole thing. And somehow notice here that this doesn't depend on the locations of the poles, right? So it doesn't matter where these, what these alphas are, it's like uniform in these alphas. And then what about ordinarity? Well, it's well known that the curve is ordinary Jacobian if and only if f has simple poles, that is, degree of f alpha is 1 for all alphas. And so this in particular follows from the Doering-Schaffer-Rewich formula, also from work of Sabrow and also recent work of Priest and Zhu. So of course, I should say here that Priest and Zhu also do a lot more. They also like write down a very nice way of they give a complete description of the P-ring stratification of the Argent-Schreier locus in terms of like combinatorial data. And so now you're sort of reduced to counting well, rational functions with square-free denominator, and so that gives you the numerator, and then you count rational functions with some extra conditions, and that gives you the denominator. Then you divide the two, and you get what you want. Okay, and so so C1 and C2 here are some explicit constants, and C1 over C2 for, so the only time this is non-zero is when p is equal to 2, and in that case you get the quantity that I wrote down earlier. Okay, and so what happens for superelliptic curves? Well, okay, so for n an odd prime and q is sufficiently large power of 2. So here when I say sufficiently large, I mean like it only depends on n. So once you fix n, this like sufficiently large power of 2 is fixed, which is why one of the reasons we need to fix the n in this picture. And so you consider the cover that's defined by this equation. And so now we can make some simplifications to this. So you write fx. So first of all, you can take fx to be nth power free by making a transformation. And then you can write this as like the product of fix to the I, where each of these fi's are square free and mutually coprime. And so what you should think of this as is the analog of writing, say, a cube-free integer in terms of a square-free integer times a square, right? So that's essentially what I'm doing here. And so this map from CF to P1, which basically sends x comma y to the x coordinate, is ramified precisely at the zeros of f and possibly at infinity. And it turns out that it's unramified over infinity if and only if the degree of f is 0 mod n. Okay, And so for simplicity of notation for this talk, we will assume that CF is unramified over infinity. And in particular, so all of this works even if it's ramified over infinity. It's just, it's cleaner to state it in this case. That's all. There's like analogs for not for being ramified over infinity. Okay, and so this brings us to, well, how do you actually calculate these? How do you determine when a curve like this is ordinary? So for this, we use the work of Elkin. So for that, again, this is something that has come up before, which is the Cartier operator, right? Which is a semilinear operator on the space of differentials of any variety in characteristic P. And the Cartier operator is known to be related to the A number. So the co-rank of the Cartier operator is the A number. And so in particular, if you want ordinary things, you're looking for full matrices. And so if you use the work of Elkin on the rank of the Cartier operator, you can show the following proposition, which is that if you have this map, which is unramified over infinity, then the curve is ordinary if and only if the degree of fi is equal to the degree of fn minus I for all I. So recall here fi's and fn minus i's was the decomposition in terms of square-free polynomials. So I should say something about the proof here. So what Elkin does is that they look at the action. So first of all, because a superelliptic curve, so let's say CF, so this is a superelliptic curve, this comes with an action of the roots of the nth roots of unity, right? So this the space of differentials also breaks up into very nice eigenspaces of this action. And so what Elkin does is they compute the action, or they describe the action of the Cartier operator on each of these eigenspaces, and then describe the rank in those terms, in terms of the dimensions of these eigenspaces. And so using that, you can show with some with some amount of work that the curve is ordinary if and only if this sort of criterion is satisfied. And then in order to count such polynomials, we use results of Bukur, David, Fagon, and Aline from 2009. This is, again, something that Alina mentioned in her talk, but we don't use their main result. We just, it's like one of the lemmas in their paper. And so using their work, you can actually count these polynomials. And what that gives you is that it gives you an upper bound on the number of ordinary curves. So the upper bound for the number of ordinary curves is given by this quantity here. So it's x log x to the n minus 3 over 2. And so recall here that n is mod prime and q is some power of 2. And the total number of superelliptic curves is bounded below by this quantity. And so it turns out that upper and lower bounds are the only things you need for showing that something is 0. And so this, as x goes to infinity, this thing goes to 0. Okay. Wait, okay. I went way faster than I thought I would. Okay, so just to wrap up, so just like in terms of, so this is like a callback to some of the other talks in this in the conference. So for one of the things is that if you're only interested in P ranks, right? So so things that are like isogeny invariant, essentially, you can try to instead look at wave polynomials or study like the size of CFQ, for instance, and see if that can give you some sort of information about the probability of ordinarity and or like the distribution of P ranks. So this is work in progress for these hyperelliptic curves, mostly because a lot is known about the distribution of CFQ for hyperelliptic curves. This is again something that Alina mentioned in her talk, which is the work of Kurlberg and Rudnick. which describes this, which also gives you like some information about the higher moments of this quantity. And so you can use that as input and try to say something about P ranks. There's that. You can also ask, do the case Ellenberg, Zurich, Brown heuristics hold for curves or abelian varieties with full monodromy group? So as I said before, somehow these curves are curves that have large automorphism groups, and so maybe you don't want to consider those. Maybe you want to consider things like hyperelliptic curves. But the problem with that is that somehow we don't know how to prove anything for these curves, at least not in the large G limit. Okay, so like hyperelliptic curves, therefore, is like the next big step, I would think, for something like this. And all of this sort of also ties nicely into the Sarnak philosophy, right? So you could ask, why should you expect that this limit should be nice at all, right? Like, and so somehow this sort of ties in with this sort of equidistribution of Frobenius statement. So Katz and Sarnak, they have this nice result about how Frobenius is equidistributed, but that's somehow known only for the large limit. So that you get a main term and an error term, and the error term goes to 0 when Q gets large. But somehow, if you want to show a large G limit kind of equidistribution result, that's much harder. And you also, like, for example, you might need things like homological stability in order to actually prove something like that. So like equidistribution of Frobenius is like the big goal, but I don't, yeah, it's also an ambitious goal. And so so that's that. And then there's also a question about, are there modified heuristics that explain the results of this talk? Right. So for example, one of the things that again came up earlier, which is something that Professor van der Heer was talking about, which is instead of stratifying moduli space by like P ranks or stuff like that, what if you stratify it by automorphism group? Right? Is that a nice stratification? And can you use right? So if you somehow restricted to strata where these families had like some sort of uniform automorphism groups, would these families be asymptotically good, right? To use the words from the last talk. And of course, you can also ask, which is sort of like tied into like the second bullet point, which is like, is being asymptotically good related to having a large monodromy group, or is it related to being part of an irreducible locus? And okay, so I sort of went off on a little bit of a tangent there, but essentially, like, to ask for modified heuristics, as I said earlier, it doesn't seem like in characteristic 2 that unitary group statistics sort of match up with what you get for superelliptic curves in characteristic 2. But again, as I said earlier, I don't know if this is a low characteristic issue. And lastly, okay, this is, people might be offended if I say something like this, but maybe for reducible loci, you don't want to consider the genus, right? Like, you want to order by something other than the genus. Like if you're considering Artin-Schreier curves, like maybe the thing to look at is not as some genus goes to infinity. I'm not brave enough to volunteer a guess of what should replace it, but maybe there's some other kind of height function on the Artin-Schreier locus. Okay, so I think I'll stop there, and I think I finished much earlier than I thought I would. All right, thank you for listening, and thank you to the organizers once again for inviting me and for organizing such a great conference.
Thank you, Soumya. Questions, remarks?
Yeah, I have a question. Oh, sorry, go ahead.
No, go on, please.
Oh, hey. Yeah, so from this we see that the P rank equals G, Arden-Schreier curves or superelliptic curves have density 0. But what can you say about the other P ranks in these families?
Right. Okay. So in these families, as I said, so it sort of like ties into the last thing that I said, which I wasn't very clear about, perhaps, is that so in these families, if you look at other P ranks, you will also get 0. So the right thing to measure in that case is not really the P rank, but maybe something like, okay, so maybe what you want to say is that you look at the P rank and then you divide it by G and say, okay, what is the probability that this lands inside a certain interval? You have to like place some lower bound on what the lower part of the interval is. So there's like, yeah, so one can probably say something about this. So I think that it's doable. It just hasn't been done.
Like,
but,
well, for
yeah.
example, like would the P rank be 0? Would that, like if you just let it be 0, like what density might, do you think that would be like positive?
Oh no, you won't get positive things. So for the Arden-Schreier locus at least, if you take any other P rank and say, okay, what is the probability that an Arden-Schreier curve has P rank equal to S, that will be 0.
Okay.
Yeah.
Thank you.
So essentially what you want to consider is something like, what is the probability that an Arden-Schreier curve has P rank bigger than or equal to something, right? So that is the kind of question that you want to ask. And there's like partial results towards that. In that, I think, so I did like work out a lower bound, which I don't remember off the top of my head because it doesn't look very nice. But yeah, you don't, there's like no complete result.
The formula you give, I mean, they are for what you call the natural counts. That means you count really polynomials, right? Or
yes, that's.
But
I end up counting polynomials.
Okay, but I guess, I mean, if you would take isomorphism classes, it would not change that much in that
No,
case.
it wouldn't. At least for p greater than or equal to 70, you can definitely show that it doesn't change. I think for like p equal to 3 or 5, I would also expect that it doesn't. So this, yeah. So, but for p equal to 2, my guess is it might change.
And,
yeah.
Okay. And just like a very naive question, you said, I mean, after like trying sp2g, you went to the unitary group, but it didn't work. I'm just wondering, I mean, and it's super naive. I mean, the people who study the Satotate, I mean, they have also a bunch of groups that show up. I mean, if you would just lift your, I mean, take your curve and consider it over a number field, and then, I mean, there would be a group associated to this family. Wouldn't that be the group that one should consider? Maybe it's super naive, sorry. But
No, that's a good, no, probably, yeah, maybe. I'm not sure that, okay, so here's my concern. My concern is that they would still give me a non-zero probability. Like the point is that like getting 0 out of these kind of statistics, like it seems unlikely. However, I don't off the top of my head know what the Satotate group is for this particular thing. I'm not very familiar with that part. So, but maybe that, but yeah, that's a great thing to try. Yeah, definitely.
No, I mean, really, yeah. I mean, I have no idea why you should like look for this kind of groups, but just the relation with the Satotate looked for me like something to try.
No, that's totally fair. Yeah. The thing with the superelliptic case is that it could be a coincidence of small characteristic, and I'm not sure if it is.
No, and that's all, Christoph. Then Andrew has a question.
Yeah, just to follow up on what Christoph said, I think the and Francesc might know more about this, but I think you can work out the Alatic monodromy group, which will tell you which determines the Satotate group. But I think you're probably right to be cautious in small characteristic. There might be an issue there. But like for the Picard curves, just as a special case, we know that the subtape would be the normalizer, either U1, sorry, U3 or the normalizer of U3 is embedded inside USP6. And from that, you could probably at least get a heuristic that would tell you what the distribution should be. But I think Francesc Vite has thought about this a lot more than I have.
I see.
But I also had just a small question. I noticed you were careful in your definition of superelliptic curve to require the degree of f and the n or the d, whichever it was, to be co-prime. And I was wondering, where did you need that? Because I think the Elkin result is more general. It works for arbitrary cyclic covers.
Yes. So yeah, I needed n to be an odd prime. It's just that. So the Elkin result does work, but to go from there to the degree criterion, it's like it's combinatorial, and the combinatorics just gets more hairy. So it might still be true, like, but it might be, it's just like more complicated. I think the results would just be more complicated. Yeah.
Thank you.
Thank you. Other questions? I have a remark on Katsarnok philosophy that it looks quite plausible that for abelian variety, it might be true for G limit as well, though I have no idea why it should be true, but it's definitely wrong for curves. So if you consider only Jacobins, then the Frobenius is by no means a random matrix, because if it were, we would have quite a different distribution of Frobenius values at the limit. And we know that for curves, it differs a lot from what we see for abelian varieties.
I see. Okay. Is there a reference for what is this?
You may have a look at for abelian varieties. You may have a look at Serge Stork at Bourbaki seminar, and for curves on our paper with Vladutz. Either the one quoted by Hajir or the previous one on the function field case only.
Okay. Awesome. Thank you so much.
Well, it isn't, nothing is said explicitly, because the questions in those papers were different, but it looks that it's totally impossible for curves.
I see. Okay. Yeah.
But, because in some sense, if it were, the number of points could be negative.
Okay. Yeah. Okay. That makes sense.
Good.
Yeah. So would you expect that like there is a different kind of group that governs the distribution, or that it's just not true that it's going to be?
I don't see any group there.
Okay.
It looks that for abelian varieties, you do see a group, but the Jacobins are, in the sense of that group, the Jacobins are, the fact of being a Jacobin is a queer notion in some sense. So,
all right. Okay. A little bit better. Thank you. Yeah.
Welcome. Other questions or remarks? If not, we thank Soumya again. And we'll have a break of 1 hour, 10 minutes. And before we go for that break, I would like to thank the organizer on my behalf. It was a really very good conference. So thanks a lot.
Thanks a lot, Misha.
Thank you. Michael,
Thank you,
may
Antonio.
I ask you about the raya behind you? Is that a raya or a latch hook rug?
That's a carpet.
It's a carpet.
Yeah, that's a carpet given to me for my 50th birthday by a late friend of mine.
It's great.
Yeah, thank you.